In previous videos, we have seen how the Legendre differential equation, which is reproduced here, can be solved using the method of regular series expansions. And we get the primary solution, which is PLX, the nth degree Legendre polynomial in X. There is a problem with the singular solution. A second order differential equation needs to have two independent solutions by the existence and uniqueness theorem of Cauchy. So where's the second solution? We already know that there are going to be two solutions, the even and odd polynomial for each value of L, and for a specific value of L, only that kind of polynomial survives. For example, P1, only the odd polynomial solution truncates, and the even order polynomial solution diverges at plus or minus 1. So as a result of that, we are forced to only have one solution. Well, where does our second solution reside, and how can we find it? Fortunately for us, we have already laid the groundwork to find the second solution if we know one of the solutions, and that is the method of Bernoulli. Go back to the previous videos and see how the Bernoulli's method is used in a general situation. What I will do now is I will write this in line with Bernoulli's method. So Bernoulli's method requires us to write the coefficients in such a fashion that there is no coefficient with respect to y double prime, there's some function with respect to y prime, and there's another function with respect to y. And I'm going to keep the same notation that I used when I was talking about Bernoulli's method. Now to bring this to this form, all we have to do is divide both sides. So what I'll do here, I'll divide y double prime by 1 minus x squared. So that's a negative 2x. I'll try to absorb the negative sign by making the 1 minus x squared minus 1. And then this term is L times L plus 1 divided by 1 minus x squared, y equal to 0. So this is a one-to-one correspondence, and we can apply the fruits of our labor when we studied the Bernoulli method. Remember that for the Bernoulli method to take off, you write y as u times v, and then I'm going to favor the u function, so I'll end up getting u double prime. And again, for the details, you go to the Bernoulli video. 2v prime over v plus p1 u prime plus v double prime plus p1 v prime plus p2v divided by v times u equal to 0. Now, I mentioned during the Bernoulli video that there are two possibilities. One is that we know one of the solutions, v. In that case, this term disappears. Well, that is the precise circumstance that we find ourselves with right now, because we do know one of the solutions of the Legendre differential equation, and that is PLX. So we are going to assume that v is in fact PLX. If v is PLX, then it's going to satisfy the Legendre differential equation, and so this term is going to simply disappear. And I'm going to end up getting just this. I'm going to call this in line with what we called it when we espoused the Bernoulli method. I'm going to call it Q of x. Also, I'm going to set the u prime equal to something. Let's call u prime equals w to reduce the order. So then I get w prime, where w is still a function of x, by the way. So I get w prime plus qw equals 0. Well, that's a rather easy differential equation to deal with, because that's just dw by dx equals minus qw, which can be separated, and I get dw over w equals negative q dx. And integrating both sides, I get natural log of w equals e to the negative integral q dx. Sorry, that's just w. That's natural log of w, and then w will be exponential. So I did too many steps at once. And there's a constant which I'm not going to truly worry about at this stage. I'll include it at the end. So that's going to be our w. But w is not, we're not done with w yet, because we have to talk about w being u prime. So let's integrate again. So u will be equal to the integral of w dx. So that's going to be the integral of e to the minus integral q dx dx. Okay, and now I'll put plus c. All right. I should probably put the c here, put a c here and a c1 here. So now I have c here and c1. Okay, that looks better. Lastly, the full solution is u times v, so I'm going to get the y of x, which is equal to u times v, is cv integral e to the minus integral q dx plus c1v. Well, what is v? V is plx, so I'm going to substitute that. So I get c plx integral e to the minus integral q dx plus c1 plx. So it looks like there's a plx in both places, but there's this integral also. So this is not going to be polynomial. These are not going to be polynomials. They're going to be some pretty nasty things. This part is polynomial, so that's the solution to the Legendre differential equation we got from the previous developments, but this is a new kid on the block. Rather than keep writing this unwieldy thing, people sometimes call it QLX. And written like that, it's called the associated Legendre functions. Notice that the term polynomial is not used because it simply is not a polynomial. These are polynomials, these are functions, because this is in general a pretty nasty integral. What is that nasty integral? Let's find it next. To do that, we will have to break down what integral q dx is. So let's work on that next. The integral of, so I'll just do this, negative integral q dx first. Well, that is, if you notice what q is, it is 2v prime over v plus p1. Okay, so that's going to be negative 2 times the integral of v prime. V prime would be the derivative of p, so that's going to be dp L over dx divided by just PL, the whole thing times dx. And then also a term P1. P1 is this. So that's going to be minus the integral of 2x dx divided by x squared minus 1. Observe some nice simplifications. This dpl over dx times dx over pl is just dpl over pl. So that gives me negative 2 times the natural log of pl. And this, if the denominator is set equal to some substitution, like u substitution, I'm afraid to call it u because I've already used u here. So just think about it as a quantity. if that's some quantity, that's a derivative of that quantity. So this is also negative natural log of x squared minus 1. I put the absolute value sign because x is in the range of -1 to 1, so sometimes this can be negative. So put the absolute value sign to protect yourself. Well, that's just natural log of negative natural log of p squared by the property of natural logs. And then I'm going to get negative natural log x squared minus 1, and by the property of natural logs, that's just natural log of the product of those two things. So I can put a big absolute value sign and not worry about it anymore. That is PL of x squared times x squared minus 1. Please don't think of it as the polynomial as a function of x squared minus 1. That's the danger of writing it like this. All right, so now I have evaluated this. So e to the power minus integral q dx is what we really need, because that's what shows up in the associated Legendre functions. So remember that exponential and natural logs are natural enemies. So when I do e to the minus, that minus cancels with this minus, so I simply get e to the natural log of plx. So that's going to be maybe I can write one more step before I do that. So this could be written as natural log of 1 divided by PL squared x squared minus 1. And all that is equal to negative integral q dx. Now raising both sides to the power e, I'm going to get 1 over absolute value of PL squared times x squared minus 1. So that's our integral. And so now we have a compact formula for the associated Legendre functions. And that formula is this. The constant is never written. It's constant. So the full solution is going to be a constant times QLX plus another constant times PLX. That will be the full solution of the Legendre differential equation, where QLX, drum roll, is equal to PLX times the integral dx over PL squared 1 minus x squared. Now here I want to forever remove the absolute value bars. I know that x is going to lie between -1 and 1, not including the endpoints. So rather than write absolute value of x squared minus 1, I have just removed the absolute value bar and written it as 1 minus x squared. That's always guaranteed to be positive. So in this fashion, we have found the second linearly independent solution of the second order equation known as the Legendre differential equation, and I've completely solved it in every possible detail.